Hi, this is Mrs. Basin, and today we're going to talk about the gas laws. So the gas laws have to do with the behavior of gases. What we're going to look at today are the mathematical relationships between all of those properties that we've been talking about. So they're named after the scientists that came up with them. So the first one we're going to look at is Boyle's law. So Boyle's law shows the relationship between pressure and volume when temperature and the amount of gas is constant. So the mathematical relationship is P1V1 equals P2V2. So like you saw in the lab and the activities that we've done in class, pressure and volume are inversely related. So as one increases, the other one decreases. So with that law, P1V1 equals P2V2, we can solve for a variable given the other three. So this is how this would be applied. So it says we have a cylinder that has a movable piston with an applied pressure of 4 atm. So what we're going to do as we learn how to do the math for these gas laws is in the problem, we're going to make a list of everything that's given, because once we go through a couple of these, you'll see how you're going to have to make a choice about which gas law to use. So for this one, it says it has a pressure of 4 atm. So I'm going to write that as my pressure. And it has a volume of 6 liters. I want to know what is the new volume. So I'm going to call these P1V1. So my new volume is what I'm going to solve for when the new pressure, so I'm going to label this as P2, is decreased to 1 atm. So this tells me the relationship that I'm looking for here is P1V1 equals P2V2. So all I have to do to solve this is to sub in those variables. So P1 was 4 atm, V1 was 6 liters, P2 was 1 atm, and V2 is what I'm solving for. Now, when we do these gas laws, the pressure that's given, it doesn't matter what the pressure is as long as the initial and the final pressure are the same. Same goes for volume. So it doesn't matter which unit it is as long as the initial and the final volume are the same unit. So for this one, this is just like an algebra problem, so all I'm doing is solving for V2. So I'm going to multiply 4 times 6 divided by 1. So V2 for this one is going to be 24 liters. We still use our sig fig rules, so all of these have 2 sig figs, so my answer is going to have 2 sig figs. The next law we're going to look at is something called Charles' law. So Charles' law shows the relationship between temperature and volume when pressure and the amount of gas is constant. So the mathematical relationship here is V1 over T1 equals V2 over T2. And like you saw in the experiments we did in class, as one increases, the other one increases. So these are directly related. For these, anytime you use temperature in gas laws, temperature has to be in Kelvin. So Kelvin is a temperature scale that we don't normally use because of the vastness of the scale. But to get to Kelvin, you're going to add 273 to the Celsius temperature. And we'll see how that works in just a minute here. So we're going to approach this one the same way as we did the other one. So it says we have a sample of gas that has a volume, so I'm going to call that my initial volume, of 2.80 liters at an unknown temperature. So the initial temperature, I don't know. Then it says when the sample is submerged in ice water at 0 degrees Celsius, so that's my second temperature, its new volume, or its volume, decreases to 2.57 liters. So then this tells me I need my formula that relates volume and temperature. So based on what we just looked at, I know V1 over T1 equals V2 over T2. So same deal here. I'm going to sub in my variables. So 2.80 liters over T1, because T1 is what I'm solving for. V2, this one's okay because the units are the same. So your first and your initial and your final have to be the same unit. So this one is still liters. So 2.57 liters over T2. And like we said, temperature has to be in Kelvin. So we're going to take this 0 degrees Celsius and we're going to add 273. So that gives me 273 as my Kelvin temperature. Same thing here, solve for T1, and probably the easiest way is to think of it as cross-multiplying. So I'm going to take 2.80 times 273 divided by 2.57, and that gives me a T1 of 297 Kelvin. Now the problem says it wants the initial temperature in Celsius. So to get it to Celsius, I'm going to subtract that 273 that I added originally. So that leaves me with 24 degrees Celsius. So the next law we're going to talk about is Lew Sachs Law. And his law shows the relationship between temperature and pressure when volume and the amount of gas is constant. Again, this relationship is also direct, so as one increases, the other one increases. And just like before, temperature has to be in Kelvin. So here's an example for this one. It says a sample of gas with an initial pressure, so that's my P1, of 725 millimeters of mercury. So this is a different unit for gases. And a temperature of 305 Kelvin. Okay, and again, this time I don't have to change it because it's already in Kelvin. Is warmed to a temperature, so now I have a new temperature of 375 Kelvin, and I want to know what is the final pressure. So the relationship between pressure and temperature is P1 over T1 equals P2 over T2. Sub in my variables, 725 millimeters of mercury divided by 305 Kelvin. P2 is what I'm solving for. T2, again, already in Kelvin, 375 Kelvin. So again, do your algebra, solve for P2, 3 sig figs, so it ends up at 891 millimeters of mercury. And I know what the final unit is, because it's going to be the same as whatever the initial unit was. So when you're trying to figure out what the final unit is for volume or pressure or temperature, you always look back to see what the initial one was given, or the other one in the problem was. So the last one we're going to look at before we combine all of them together is one called Avogadro's Law. And this is the same Avogadro that we've talked about before. So Avogadro's Law shows the relationship between volume and the amount of gas, or the numbers of moles of gas, when pressure and temperature are constant. This is also a direct relationship. So as one increases, the other increases. So here's an example of this one. We have a 4.8 liter sample of helium gas. So that's a volume. So that's my initial volume. And it contains 0.22 moles of helium. I want to know how many additional moles of helium need to be added to get a new volume of 6.4 liters. So I'm looking for N2. So relationship I just looked at was V1 over N1 equals V2 over N2. Again, same unit, so we don't have to change anything there. 4.8 liters. N has to be in moles. So if they gave you the amount of gas in grams, you would have to do a molar mass conversion to get to moles. But this one already gave it to us in moles. So 0.22 moles. The new volume that we want is 6.4 liters. So I'm looking for N2, or the new number of moles. So again, do your math. N2 ends up being 0.29 moles. So that's the new number of moles, but I have to be careful with these because this particular one says how many additional moles need to be added. So if I started with 0.22 and I need 0.29, if I subtract that original, then I would need 0.07 moles added. You're not always going to have to do that, but just like we learned in the last unit, you have to read very carefully to see what it's asking for. Same thing will apply in this chapter and this unit as well. So it wants to know, if it just asks what is the new number of moles, you could have stopped after the 0.29, but because this one was asking how many additional moles, we had to subtract out what we started with to see how many additional ones we needed to add. Okay, so the last thing we're going to look at is something called the combined gas law. All the combined gas law does is it puts all of these relationships together. So this is really the only formula that you need to know, and then you just take out any of the substances that are held constant, and you're left with all of those individual laws that we just talked about. So just like before, anytime you use a gas law formula, temperature has to be in Kelvin. But if you notice, if we look at pieces of these, you can see Boyle's law, P1V1 equals P2V2. You can see Charles' law, V1 over T1 equals V2 over T2. Lew Sachs Law, P1 over T1 is P2 over T2. And Avogadro's law, V1 over N1 equals V2 over N2. So all of those laws are combined within this, but if you just use this one law, eliminate anything that is constant, and you can assume if it's not mentioned in the problem, then it's constant, and you're left with the law you need. Now, it is possible that you could have more than just two variables involved. So you might have 3 of these on each side, and you could even have 4 of these on each side. Okay, so here's an example of this one. And this is why we talked about in the very beginning how you're going to make a list of the variables as you read through the problem, because then that will let you know which parts of that formula you need. Okay, so it says the initial volume, so V1 is 158 milliliters. Initial pressure is 735 millimeters of mercury, and a temperature of 34 degrees Celsius. The gas is compressed to a new volume of 108 milliliters, and it's heated to a new temperature of 85 degrees Celsius. I want to know what is its final pressure. Okay, so let's look at that whole combined gas law again so we can kind of see what we mean by taking out what we don't need. So P1V1 over N1T1 equals P2V2 over N2T2. So this one mentions pressure, volume, and temperature. So that means I can assume that moles is constant, so I can take it out of the formula. So for this one, the only part of that I need is P1 V1 over T1 equals P2 V2 over T2. Okay, before I sub those in, I have to take care of my temperatures. So the temperatures need to have 273 added to get those to Kelvin. And then I can sub everything in. Volume is the same unit, milliliters, milliliters. Temperature, Kelvin and Kelvin. And then when I solve for pressure, it'll be in millimeters of mercury. So 735 mmHg times 158 milliliters divided by T1, which is 307 Kelvin, equals P2 times 108 milliliters divided by 358 Kelvin. Again, do your algebra, solve for P2, and you end up with 1,254. Since we have 3 sig figs, and actually we have 2 sig figs here, so we can round it to 2 sig figs. So we would round that to 1,300. Unit for that, we would go back and look and see what our original pressure unit is. So we would use millimeters of mercury. So 1,300 mmHg.